Hi everyone. Today we're going to be beginning our notes on 2.6 even and odd functions. I want to start by just presenting a few examples of both even and odd functions. On the left-hand side, we see three examples of even functions. What do you notice about these graphs? What are some things that all three of these graphs have in common? On the right-hand side, we have some odd functions. We have three examples here. Again, what do you notice about these three graphs? What do all of these three graphs have in common? And finally, if you scroll down, here are three graphs that are neither even nor odd. So what do these three graphs not have that either even or odd has? So we're going to generalize these things. So if you take a look at even functions, you might notice that all of these graphs are symmetrical about the y-axis. If you were to draw in like a line at x equals 0, the y-axis, then each of the graphs have the same thing on the right-hand side as they do the left-hand side, just mirrored. For odd functions, you might notice that the positive x, or quadrants 1 and 4, are reflected over the y-axis, but then also reflected over the x-axis. So you can also think of this as a rotation 180 degrees around the coordinate plane. These functions are all odd, and this is true for all three graphs. Notice for the neither functions, or the neither graphs, these are not symmetrical about the y-axis, and they cannot be rotated 100 degrees about the origin to get the same graph, right? So the positive x side of the graph, or quadrants 1 and 4, is not mirrored over the y-axis and over the x-axis to give us the same thing in quadrants 2 and 3. Okay, so how can we tell whether a function is even or odd given the function, a table of values, or the graph of a function? We can tell that a function is even if f of x is equal to f of negative x. So we're saying that if you reflect over the y-axis, this takes us back to our transformations here, then the graph is the exact same. Or you can think for all negative x is the same as, I should say, for all of the negative x values, the function output is the same as that for the positive x values. If we were to look at a table of values here, x, f of x, then for some value a, then the function would simply evaluate to f of a. For some value negative a, the function would also evaluate to that same value, f of a. For the graph of the function, we've talked about this. It is if the graph is symmetrical over the y-axis. And by symmetrical, I mean that it's the exact same graph if you were to reflect it over the y-axis. For odd functions, we can tell that the function is odd if for f of negative x, this is equal to negative f of x. Okay, so if we take a reflection over the x-axis, that's equal to the reflection over the y-axis. I got those flipped. So a reflection over the y-axis, here we go, is equal to the reflection over the x-axis. Okay, so on a table of values, again, x, f of x, if we have a, well, then we simply have f of a. But if we evaluate the function for negative a, then that would give us negative f of a. So the function output becomes opposite sign as well as the function input. We can tell this from the graph if the graph is symmetrical about the origin. So what do I mean by that? I mean that if you were to take the graph, let's take a look at the graphs above, these odd graphs. If I were to take this graph and reflect it over the x-axis and over the y-axis, then it would land exactly onto itself, onto the original function. You can also think of this as if you were to take this right-hand piece and you were to rotate it, or I should say pivot it, around the origin 180 degrees, then you're going to land exactly in the same spot as the original. Okay? All right. So let's take a look at the actual definitions. Here we have even and odd function. For a function f, f is an even function if it satisfies f of negative x is equal to f of x for all x in the domain of f. F is odd if it satisfies f of negative x is equal to negative f of x for all x in the domain of f. So on this left-hand side, we have this U-shaped graph. This is an even function. It shows symmetry over the y-axis. For this graph on the right, we have an odd function. This shows symmetry about the origin. So let's talk even functions. A few examples of even functions. Well, our U-shaped graph, y equals x squared. Another example would be like our V-shaped graph, y equals the absolute value of x. So let's go ahead and use the algebraic test to determine if f of x and g of x are even functions. Then we're going to graph them on our graphing calculator and explain how the graphs support our conclusion. So let's start with f of x. I'm going to go ahead and just rewrite the equation right here. F of x is equal to x to the fourth plus 2x. And then in order to determine if it's even, we're going to evaluate, or I should say, write f of negative x. So now I'm going to, anywhere I see x in the original function, I'm going to plug in negative x and then simplify. Okay, so we have the quantity negative x to the fourth plus 2 times negative x. So we have negative x to the fourth. We're raising to an even power. This is equivalent to just simply x to the fourth. That negative goes away because we're raising to an even power. For 2 times negative x, this is equivalent to a negative 2x or minus 2x. So now we have to ask ourselves, does f of x equal f of negative x? And the answer is no, it does not equal. Okay, so we have x to the fourth plus 2x, and we have x to the fourth minus 2x. So these are not equal. Therefore, the original function f of x is not an even function. Okay, now let's go ahead and graph this on our graphing calculator to see if this supports our claim. So in your graphing calculator, go ahead and open up a new graph and type in the function x to the fourth plus 2x. And if we were to graph this, we can see the shape of the graph here. From the graph, we have to determine whether or not this is symmetrical over the y-axis. And I see on the left-hand side of the y-axis, it dips into the negatives, whereas on the right-hand side of the y-axis, it does not. Therefore, this function is not symmetrical over the y-axis. So that confirms our claim that f of x is not even. So let's go ahead and write. This says explain how the graph supports your conclusion. We'll say f of x is not symmetrical over the y-axis. Okay, so now let's go ahead and test g of x. So we'll start with just rewriting the function. G of x is equal to x squared minus the absolute value of x. Okay, so now let's go ahead and write out g of negative x. And so anywhere that we see x, we're going to plug in negative x. And always use parentheses, because some of these operations, like the exponents, those parentheses matter. Okay, so simplifying g of negative x, we get the quantity negative x squared. Well, that is an even power, so it's equivalent to just positive x squared. It gets rid of that negative. And then we have minus the absolute value of negative x. Well, by definition, the absolute value takes its argument and makes it positive. So this is equivalent to the absolute value of positive x. And there you have it. G of negative x is equal to g of x. So we can write that out. G of x is equal to g of negative x. Therefore, g of x is an even function. So let's go ahead and test this back on our calculator. So I'm going to hit tab, and we'll go ahead and clear out our original function. So in our function, let's go ahead and type out x squared. And then we have minus the absolute value of x. So to get the absolute value, I'm going to look at this book key on the right-hand side of my calculator. The button just to the left of that has all of our operators. So I'm going to use the absolute value. For me, it's all the way to the right on the top row. And we're going to do absolute value of x. Let's go ahead and enter that. And I can see that in this graph, the right-hand side of the graph, I should say right of the y-axis, is symmetrical with the left-hand side of the y-axis. It's the same function on both sides. So our graph confirms that g of x is an even function. So let's go ahead and write g of x is symmetrical over the y-axis. Okay. All right, on to number 2. Fill in the missing portion of the graph, and the table of g of x and h of x are all even functions. Okay, so For this first one, we have g of x, the graph. We want it to be an even function. So I know that on the graph, this shows up as a reflection over the y-axis. So I'm going to take the same points, the positive x values, and then make them negative. So instead of the point positive 1, 0, I have negative 1, 0. Instead of the point 2, 1, I have negative 2, 1. Instead of 3, 0, I have negative 3, 0. And then it looks like we also have like 4, 3. So I'm going to do like negative 4, 3. Okay, so let's go ahead and sketch this shape of the graph. It comes down from the y-axis, and it kind of bounces up onto the over the x-axis, and then comes back down, and then it shoots back up. So we've got like this function here. So now we can see that this function is symmetrical over the y-axis. So for h of x, we need to have h of x equal to h of negative x. So this is by definition what an even function is. So then if I know that h of negative x, I'm looking at negative 3. If I were to take negative 3 and make it negative, I would get positive 3. And I know that those outputs should be the same. So for both positive 3, h of positive 3, and h of negative 3, the output should be negative 5. Likewise, the same is true for positive 1 and negative 1. H of negative 1 is equal to h of positive 1. Therefore, the outputs are, again, the same. So negative 3. Okay? Go ahead and flip the page. Now let's talk about odd functions. So we'll start with some examples. Some examples of odd functions are y cubed. Y equals x cubed. There we go. Y equals x is an odd function. And even like y equals the cube root of x. Those are all odd functions. So number 3, let's use the algebraic test to determine if f of x and g of x are odd functions. We're going to graph them and explain how that supports our conclusion. So remember, in order for a function to be odd, then we have to have f of negative x is equal to negative f of x. Okay, so let's start. I'm just going to write out f of x, which rewriting it is x cubed plus 2x. So therefore, f of negative x, anywhere that I see an x, I'm going to plug in a negative x. So we get the quantity negative x cubed plus 2 times negative x. So go ahead and simplify negative x cubed. We're raising to an odd power, so this is equivalent to just negative x cubed. And then we have plus 2 times negative x is negative 2x. So I'm going to say minus 2x instead. So let's go ahead and evaluate, or I should say simplify it, negative f of x. So we're going to take a negative and we're going to put it in front of the entire f of x function. So x cubed plus 2x. And use parentheses when you put that negative out in front. When we use parentheses, we're going to distribute that negative. We get negative x cubed minus 2x. Now, are f of x and negative f of x the same? Yes, they are. Therefore, f of x is an odd function. Okay, so let's go ahead and graph it and just see how that supports our claim. So again, we have x cubed plus 2x. I'm going to hit tab, and let's go ahead and remove our old function. So x cubed minus 2x, and we'll see what that looks like. So over here, we see that if we were to reflect this function over the y-axis and over the x-axis, we would have the same thing. Or if you were to take the function and rotate it around the plane 180 degrees about the origin, this function would again be the exact same. So therefore, this function is an odd function. We've confirmed our algebra. So let's go ahead and say f of x is symmetrical about the origin. Okay, let's test g of x. So g of x is equal to 1 over x. So g of negative x, again, we're going to just plug in negative x anywhere that we see x. So we get negative 1 over x. Now if I wanted to simplify negative g of x, then I'm going to take a negative and put it out in front of 1 over x. And again, we get the quantity negative 1 over x. So therefore, g of negative x is equal to negative g of x. So therefore, 1 over x, or g of x, is an odd function. Okay. And last, let's check out the graph. So going back to our calculator, and we'll remove that last one. We'll say 1 over x. Okay, so we have this function here. Again, if we were to take this part in quadrant 1 and we were to reflect it over the y-axis and reflect it over the x-axis, we would get exactly what we have in quadrant 3. Okay, you can also rotate this graph 180 degrees about the origin, and this function would be the exact same. So therefore, g of x is symmetrical about the origin. Okay. All right, last problem here. Number 4, fill in the missing portion of the graph and of the table of g of x and h of x are all odd functions. So we'll start with g of x. This is symmetrical about the origin. So we're going to rotate g of x 180 degrees or reflect over the x and y axes. So I notice that we have the point 0, 0. We've got the point 2, 4. So we also have the point -2, -4. We have the point 4, 0. So we have the point -4, 0. And then you could also say that we have the point, I don't know, maybe 5, 5. So we have -5, -5. That'd be like down here. So go ahead and sketch in that curve. It bounces off the x-axis. There you go. It's something like that. Okay. For h of x, again, we need h of negative x to be equal to negative h of x. So let's take a look at this first one. So if I were to take -3 and I were to take h of negative x, that's saying h of -3, which is h of 3. So then we're looking at h of 3, which is -5. Make it negative for a negative h of x, and we get +5. So then h of -3 is equal to 5. For h of -1, we're going to plug in -1 here into h of negative x, and we get h of -1, which is h of 1, and then is equal to negative h of x. Well, h of x is -3, make it negative is +3. Okay? So you might notice that all of our y values and x values are kind of flipped, opposite signs as one another. All right, so we're going to get a lot of practice on this. This was even and odd functions. We'll see you tomorrow in class. Goodbye, everyone.